I think we are ready to start. Okay, first of all, welcome everyone. Good afternoon. Thank you all for joining the webinar about the economic impact of lightning strikes on wind turbines. As a little side note, this webinar will be recorded as well for educational purposes. For the introduction, for the past 5 months, we have been working on a project for our international business study about the economic impact of lightning strikes on wind turbines, and we are happy to be able to finish it with an insightful webinar with speakers from different sides of the field. Jobitech, WeatherGuard and Taruka will be sharing their expertise about the topic in this webinar. If any questions come up during the presentations of any of the speakers, please feel free to put them in the chat, and we will go over them after each presentation. So starting with our first speaker today, I'll introduce him. His name is Peter Johansson. He is the founder of Jobitech and the inventor of a number of ideas and patents within the area of electrical measurements and lightning. Jobitech was founded in 1997 and installed simple lightning sensors on the world's first offshore turbine park located in Denmark. Basis for the first installations was a university project involving full-scale tower tests at the university in Aalborg in Denmark. Many turbine manufacturers, including Siemens, have been using the sensors ever since, as they have been shown to be very reliable. In parallel, the company has also made the world's first current sensors that can measure current individually in 3-wire power cables. All the sensors are based on the good old laws of magnetism explored by an even older Danish person, Mr. Ørsted. Okay, Peter, you are free to share your screen if you want, and good luck.
Thank you, and I'll find my screen here. Here we go. Yes, and thank you for the invitation. Actually, I would like to talk about the different phenomena that we see in nearby a turbine tower. And as you all know, we have a million photos, but a few drawings. So I start with a drawing here. And it's quite easy to see that we have a sky coming in. It's not good because it really would like to hit the turbine. And we all know that this is a long history. Ever since the first turbines was raised, we have seen different kinds of issues arising from especially lightning strikes. So I would like to give a technical introduction of the problems, and then I'll give a few lines about the economy that follows. First of all, I would like to talk about the physics of a strike, and I'm pretty sure that there are many opinions about that, many good and many bad stories. But our research is based on the fact that we do have some electrical charts up in the heavens somewhere. And surprisingly, there's all year round a current running from the outer atmosphere down to Earth of roughly 2000 amps all around the world. So sometimes charts is also collected inside the skies, especially having one charts at the top and the opposite charts at the bottom of the sky. And suddenly the sky would like to have the same potential as the ground, as the Earth. And what we see is a plasma channel that will act as a conductor. Then we see the flash and we hear the boom. Now we have a strike. And you have all tried to count the seconds from you see the light until you hear the boom, just due to the speed of sound. So if we look at the physics, then we have a number of places or subjects where we see the problem. In all turbines, we do have a down conducting system, and we do have some receptors at the end, often in the tip end, but also down the blade at different locations to catch the light so that the current will pass into the nacelle area and down through the tower to the ground. And sometimes we see a melting of the receptors, and that is not that good. We also see damages to some other points if the strike would like to enter at the nacelle, for example. And we do see issues like heating of wires and connectors. And finally, we also see some induced voltages. Those 4 areas I will walk through in what I'm going to present here. So if we look at the nature of lightning currents, then it seems that we have a current that rises up pretty fast, roughly 1 to 10 microseconds in rise time, and we see a peak current that could easily be more than up to 200 kiloamps or more. So it's quite dramatic what happens here. Then in the very old days, even before 1997 or so, some clever people sat down and tried to calculate or estimate how big strikes they are. And they figured out the table that you can see here that for the 98% of the strikes will be below 200 kiloamps and also below 300 Coulomb, etc., etc. So for that reason, in the standards, if turbines can meet this 98% level, then they are designed in a nice way. If the strikes are stronger than that, then quite often the insurance companies would say that then it's force majeure situation, so we are not going to cover that. But that's another long story. So the receptors that are often placed at the tip end, what happens when we see some melting here? We see that the receptors themselves, they are made of steel or copper or aluminium or some other conducting material. And when the strike hits, then some material due to the plasma and the air pressure actually brings the material to the melting point. And then not only the receptor will be damaged, but also the fibers that are nearby. So it's pretty important to make to see if they are damaged when the strike comes in. And that's where it's quite important that we have some lightning sensors to detect that situation. We have to bear in mind that the tip speed is 300 to 400 kilometers per hour. So it's really a strong wind we have here. So if there's just a small crack in the fiber material, that can easily develop as a dramatic damage at the end. So we can also have that the strike hits somewhere down the blade, and that's quite often due to bad design. If you have some sharp edges in the down conducting system, then sharp edges can attract the lightning strike to enter. Then we see holes in the fiber, as you can see on the picture here. So this is really a bad situation. There has been made an enormous amount of tests to avoid this situation, but it's still an issue out there. Then if we have some poor connections along the down conductor, then we can see heating of the down conductor material and the interconnections. If some interconnections are not really attached as they should, then for sure there will be an ignition. It functions as a spark gap, and at that ignition we'll see a small explosion. This is okay if we are in free air, but if we are within some fiber material, then it's a bad situation. Then comes to the problem of induced voltages, and that's where we have the reference to the good old Hans Christian Ørsted, because he figured out that if we have an electrical current, then we'll see a magnetic field that will arise. And the surprising thing is that actually nothing can stop that magnetic field. Many people, even many engineers, strongly believe that if they use really good EMC type boxes, then we can stop the magnetic field. But this is not true. So when a high current that is changing in time, and this is what happens here, we have a dramatic rise time, then we'll have a magnetic field that actually changes. So, and this field will pass whatever material you might have. Then some people might say, if I use iron, then it's not a big issue because iron will be like a conductor for the magnetic field, so that it will act or it will make sure that the magnetic field lines will pass outside this iron box. This is also not true, because when we come up in frequency, if the rise time is very fast, then actually iron will not stop the magnetic field. So also quite surprising to most engineers. So what happens if we have a changing magnetic field that passes some kind of a loop? And a loop, what is a loop? Well, in many places within a turbine, you have different kinds of loops that you actually do not think about. It could be a loop actually from the blade, where you have, if you have two parallel conductors on the blade and one end is not connected, then you have a loop. And if you have a loop and you have a changing magnetic field, you will also have a voltage that rises up. So if you have a voltage that rises up to a level where we do not wish to have it, then we might damage something. And if we talk about a blade, we could easily have many kilovolts of voltage by this kind of induction. We can make some calculations on that. I'll not go into that much details for this, but for sure we'll have a dramatic increase in voltage as the rise time increases. That's the d phi dt, and it depends on the area that the magnetic field lines will pass. Actually, just as an example, if we have a very, very small electronic box having a printed circuit board where we have a small loop of 5 × 5 centimeters, and that box is in a distance in the down conductor in the tower, let's say 10 centimeters, and we assume the current and rise time 50 kiloamps per 5 microseconds, we'll see an induced voltage of 15 volts. So you can say, 15 volts is not that much, but if the electronic circuit is a small controller of some kind that is sensitive to 3 volts, then it's dramatic. And then it can easily degrade or destroy the electronics on its way down. Many electronic circuits do have capacitors, and capacitors do not like to have overvoltage too many times, and then they will degrade, and suddenly someday they will stop working. So you can easily have damages that comes years after a major strike. And the technical conclusion is simply that we cannot stop the strikes to come in. And we can also see that we'll have damages on the structures. For sure, we are much clever today than we were 20 years ago. But we also have bigger turbines having much higher levels of investments to protect. So can we do something clever? And for sure we can. Basically, we have an IEC standard that is a pretty good document. It describes how to design, make a good design of a turbine. And as a design engineer, you really have to read very, very carefully. It also tells about the protection against magnetic fields and EMC. but it's a very, very thin, small chapter in that standard. It could be better, to be quite honest. And I have been told that actually 20% of the insurance expenses are due to lightning damages. So we still see some issues, even though we have been knowing about those things here for many, many years. But unfortunately, the standard does not specify that sensors are required. It just tells that this might be a good idea. But now we see that most manufacturers put in sensors into their turbines. Unfortunately, we have a good part of our business in China, and it seems that they are not really understanding at this point, but they have to learn it the hard way. So this standard is a good standard, but there's room for improvements, that's for sure. So if we look at the economic aspects of lightning damage, then we see a transition right now that manufacturers have been responsible for the first 5 years, and when they ask components from us as a component vendor, they also ask 5 years warranty from us. So that's fair. But now we see that the major manufacturers like Vestas, like Siemens Gamesa, like Nordics, etc., they take care of the service for many, many turbines, not only their own turbines, but the turbines in complete parks, etc., etc. So it also brings some requirements to us as sensor manufacturers, because we have to be able to deliver to many different types of turbines that we did not know about beforehand. Basically, it costs a lot of money to go out, especially offshore. A rough cost estimate for a single visit is 10,000 euro. And a new blade, it costs 500,000 or more. And we also know that if we stop production just for 1 day, it costs 10,000 euros per day. So there's an enormous amount of money that we can save if we can be more clever in design and in the sensors we use. So I think that was about the 15 minutes I had for now. But for sure, if any questions arise, just feel free to visit our web pages. Thank you.
Okay, thank you for giving us an insight in your expertise about the topic. If anyone has any questions, feel free to ask them in the chat. If there aren't any at the moment.
It was very clear.
It was all very clear. That's a good sign, of course.
Yeah.
Then I'll go back to the presentation. Maybe if any questions occur later on, you are free to ask them in the end of the webinar as well. Let's start up the presentation again. It's a bit slow on the school internet, it seems.
I say that we have a question from Yugal. I'm sorry if I don't pronounce your name correctly. Are there multiple sensors in a blade along the length, given that blade lengths are now in excess of 75 meters for some models?
Well, I didn't really get the question.
It's also in the chat if you like to read it yourself. I can say it again. Are there multiple sensors in a blade along the length, given that blade length are now in excess of 75 meters for some models?
Well, I'm not an expert in how to position receptors. We do see that some claim that only receptors in the tip end are required. Other models tell that we should have a receptor for every 20 meters down the blade due to the old 20-meter model that is explained in the standard. Maybe some of the other can tell about this situation, but we do see that receptors are positioned mostly in the tip end.
Okay. I think the presentation is loading up.
We are seeing the first page.
Yeah. Okay. So yeah, thanks for the question as well, of course, and thanks for answering it, Peter. Then we go to the next speaker of today's webinar. Our second speaker for today is Alan Hall. Alan Hall is the President and CEO of WeatherGuard Lightning Tech, based in Massachusetts in the USA. Alan has been working in the lightning protection of wind turbines and aircrafts for 20 plus years. He serves as a FAA designated engineering representative and was a senior technical specialist for Lightning Technologies Incorporated for 10 years. As a leading lightning protection expert, he designed his strike tape lightning diverter technology to protect wind turbines and aircrafts all over the world. Alan also co-hosts the Uptime Wind Energy podcast, which is available on Apple, Spotify, Google, and YouTube. So make sure to check that out as well. Alan, you can now share your screen, and good luck with your presentation.
Thank you. Just give me a second here to pull it up. Okay, everybody should be able to see the presentation. I'm Alan Hall. Thank you for inviting me. Thank you to Fontys for the invitation, for everybody who's attending today. I'm going to speak about some of the really economic impacts, and from the business side and from the engineering side, and how those two are always at combat, trying to figure out what the best options are for wind turbine lightning protection, because there's a lot of discussion about it today, and we're having a webinar today to speak about it, but it's outside of this webinar. There's daily discussions. I get phone calls all the time from around the world talking about how to protect my wind turbine, what's going on, why are we struggling, and hopefully I can answer some of those questions today. So we're in this development cycle. I look at wind turbines as just another engineering development cycle, very similar to airplanes and rockets. Right? And if you go through those development cycles, the Wright brothers went through it, where they had great success early on. They flew an airplane. It was powered. They flew for 100 feet. Yay. But several years later, they started to have a lot of crashes. But they recovered, right? And today, everybody flies today for the most part, and it's a very safe mode of transportation. And SpaceX, you can watch that, what happened in the 19th century or 20th century, now in the 21st century with SpaceX. SpaceX early on had some great rocket launches. It was really cool, but they also had kind of in the middle there, it was not good. They had rockets explode. Rockets didn't land on the launch pad like they should, and they almost went broke. They're very close to going broke. But today, it's just commonplace now, where SpaceX is launching astronauts to the space station, and wind turbines are kind of in that middle stage right now, where we're struggling a little bit with lightning protection. And that's what I want to describe today, is like, where are we, why are we here, and what things are we trying to do to move out of that space. So fiscal impact wise, and when an owner or an operator calls me, it's about the money. It's rarely about the engineering. It's about the money. How much money I'm spending to fix these blades, to fix my turbines. And, there's roughly 5% is a reasonable number of blades are damaged per year. Depends on where you are in the world, but in the United States, in certain parts of the United States, it's pretty high. In other parts of the United States, like California, it's pretty low. Right? So it varies a good bit. But $5,000 to $10,000 to repair a broken blade is pretty typical, right? And we kind of gotten used to that number, unfortunately. But the bigger impacts are when we snap off a blade. It takes a lightning strike, it does some sort of massive structural damage, the blade falls off, or the blade comes around and hits the tower, and we have a loss. So most of those blade breakages are $100,000 to $350,000 because they got to bring a crane in, they got to bring a new wind blade in and get guys up there to replace it. Those can be very expensive. And regardless if the insurance company is paying for it, the manufacturer is paying for it, or the operator is paying for it, somewhere it's a fiscal impact. And those fiscal impacts come into the cost of energy production, but also into the cost of manufacturing. So in order to lower all those costs down over time, we have to have better lightning protection. Because the problem is really, lightning is everywhere. There's 1.4 billion lightning strikes a year in the world. Now, there's more in some places and less in others. But as we're finding out, even there are lightning strikes at the North Pole. When probably the coldest place on Earth, there's lightning strikes. Now, that seems impossible. But everywhere we're going to put a wind turbine today, there is a chance of lightning. And because wind turbines are getting so massively tall, we're actually triggering a lot of those lightning strikes. So the grounds have changed, right? We're pretty much anything we do is going to cause a lightning strike to a wind turbine. We just need to be prepared for it and learn how to deal with it better than we are today. Here's one of the first problems. Wind and lightning are tied together. This is a map on the left of lightning strikes density in the United States. On the right is the wind intensity, wind speeds. So the best wind speeds are in the middle of the United States, where also you have the highest number of lightning strikes, or some really intense lightning strikes. We got fooled in the United States and also in those other parts of the world too. Early on with development of wind turbines, we put our first wind turbines in California. If you can see the map on the West Coast there, it's not a lot of lightning strikes there. Not great winds either, but not many lightning strikes. We thought, well, lightning strikes aren't going to be an issue. And then we moved to Texas. And Texas is has some of the largest wind sites, or the largest wind producer in the United States. As we can see, they're also a very strong lightning area. So those wind turbines that we designed for California got moved to Texas, and all of a sudden started having massive lightning problems. And that's when things started picking up around the 2000-ish, 2005 timeframe. And we're now 2022, and we're still dealing with some of those basic issues. So most lightning protection systems on wind turbines are essentially the lightning rod. And we always have to talk about Ben Franklin when we're talking about lightning, right? So Ben Franklin invented the lightning rod in the 1750s. And here we are 250 odd years later, and we're using it all the time. And it works. We use it because it works. We use it on buildings, churches, schools, amusement parks are full of lightning rods. It's very hard to walk down a major city without seeing lightning rods because they are super effective at controlling where lightning attaches to. They're not perfect, but they're really good. And in that sliver of between perfect and really good is where costs lie. And this is why we see these impacts to wind turbines. And let's talk about some of those things. So just to give you some perspective, a wind turbine blade, lightning protection system, the basic one you see on the 1 to 2, 3 megawatt machines, up to 5 megawatt machines, there's a lightning receptor near the tip of the blade. It's just a metal bolt, basically. And inside the blade is a cable that comes down to the nacelle and down the tower, and it goes to the ground. So it's essentially a moving lightning rod. And it has been very effective, right? And so we know that most lightning receptors do work to some level, depending on the size of the wind turbine. So we have implemented the Ben Franklin approach, and rightfully so, because we, as engineers, we know that it works. So we've implemented it. Great. And we've been testing it too, and we developed standards around it. So the IEC is essentially a group of engineers that come together and say, hey, how do we protect wind turbine blades, and how do we communicate that to the rest of the design world? Well, let's create a spec, and let's put that spec out there. And groups like DNV and others, insurance companies, say, in order to operate or use that wind turbine, we need you to test to the IEC standard, or show us that your lightning protection system works. And so the OEMs go off to the lightning labs, and there's a variety of them around the world, and they'll do lightning testing. And they'll provide a lightning report and says, hey, our blade lightning protection system works, right? There's some pictures here of some that didn't work in the laboratory environment, but these tests are not free. I think one thing that we sort of gloss over is like, oh yeah, they got to do a test. Those tests are expensive, right? I think a lot of times it's in the $30,000 US dollars, $50,000. You could easily spend $100,000 on lightning tests. If you're doing a real significant program, it'd be easy to spend $250,000 on a lightning program. It's really dependent upon what you're looking for, but it is a cost in the development of a wind turbine, and it's not inconsequential. So here we go to the business side. So us engineers, and I'm an engineer by training, like the lightning stuff. It's cool. It's really cool, right? And we can watch lightning happen, boom, 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 make all the noise and bright lights. But the reality hits when a wind turbine is sold. You got lawyers and contracts and warranties, and the force majeure comes out. That's where the expense really can get complicated, because you're bringing essentially legal into the discussion of what is a warranty, when do a warranty apply, when does it not apply. And typically right now, most wind turbine manufacturers offer 5-year warranties. That seems to be the standard. And they'll cover lightning damage as long as it doesn't go outside the IEC standards. So routine lightning strikes that cause damage, yeah, okay, we'll cover it. And if you look at the way that wind turbine operators use that warranty, they will have warranty claims consistently for those 5 years. Once the 5 years is up, most wind turbine operators historically stop maintaining the wind turbines like they would, because now the maintenance is on them and the cost is on them. So you'll see a decrease in the maintenance on the wind turbines, and they'll go through a couple of years, 2, 3, 4 years, and then about year 5, so total year 10, you'll see, oh, we need to do some upgrades. We need to get back onto the lightning protection. We need to fix those blades. And so you can't really look the other way. At some point, you're going to have to fix the damage. And that's where the economics and the people with spreadsheets and the accountants come into play, because some damage doesn't need to be fixed right away. Some does, right? So if you can continue to make power with a damaged blade, most companies will. But that doesn't make it better for the next lightning strike. So it's a really complicated process in the middle. So less expensive damage, hitting the end of the blade, burning it, cracking it. These are routine things that can be repaired relatively simply. Bigger damage, which we're seeing a lot more of recently, are blades really snapping off, falling to the ground, wind turbines catching on fire, which means essentially a complete loss. So as an owner and operator, these events are really major. And this is where I get the phone calls and the Zoom calls saying, hey, we had a blade that just got destroyed. What happened? Well, sometimes lightning is weird. And I think that's the answer, that lightning is a much widely variable system, and we only design to the 90th percentile. We don't design to the 100th percentile, we design to the 90th percentile. And that has fiscal impacts. So when we've gone through this cycle of having lightning protection on blades, and we've gone through this 10 and 20-ish year period of putting lightning protection on, and we start to see problems. As blades get bigger, we tend to have more issues with lightning protection, and the initial thrust was to add more lightning protection, and rightly so. As engineers, we have something that works really well. We're having a couple of issues. Let's just add more of it. And so if you look at more recent wind turbine blades, you see more receptors. On the blade on the left, there's actually 8 receptors, a metal tip, and then there's metal mesh further down. On the blades on the right, there's 2 receptors where they have most of the lightning strikes. So you see the industry look at the data they're getting back and the insurance claims, the warranty claims they're getting back, and making the adjustments to the design. So you're seeing a design evolution occur. The question is it fast enough? Because we are moving very quickly to offshore wind, to much bigger wind turbines, to 10, 12, 15 megawatt machines. We're getting away from the 3, 4s, and 5s and basically doubling the output. That's happening now. Because the issue is really lightning is a probability. Lightning is not certain. There's a lot of different variables in lightning. And we're having trouble trying to grasp all that. So you'd see 2 images here of just sort of how lightning attached to a tower. This is a radio tower in the States, of lightning just all over the place. Because what we see from lightning from a distance, it looks very consistent. Light, flash, boom, got it. But what really happens when you get up close, like if you're on the blade itself or on an antenna tower, it's not always the same, right? And the big image on the right, the lightning struck the side of the tower. That's an expensive lightning strike because it hit one of the antennas, the cell phone antennas, so the mobile antennas. So that gets expensive versus hitting the top where it's supposed to be. This is the same issue we're having with wind turbines. Lightning doesn't strike always the way we want it to. So we need to do a better job of it. Because lightning is multivariable. And this is an image that was taken down in Texas of a wind turbine farm where 14 wind turbines are reaching out to the sky, trying to create a lightning strike. And we're learning that more lightning strikes look like this than what is in our textbooks of blade, lightning, cloud, boom. That's not the case. In fact, a lot of the lightning strikes are triggered by the wind turbines. So knowing that, it's changing the way we're thinking about wind turbine lightning protection. Because lightning is complicated. And this is a lightning strike that happened in South Dakota early this year. This video's available on YouTube. You search around. But this lightning strike, hits the blade. You can actually see it follow the blade around as the blade rotates. And then it hits the blade behind it a couple of times. That is more the case in the United States than not. It's not one strike, boom, and it doesn't happen in microseconds. It happens in almost a second. It's a much longer event. And in that is where we have issues. So the challenge ahead is really here. We're growing our wind turbines so quickly, and we're moving offshore. We don't have necessarily, we have like an 80 to 90% grasp of what's going on wind turbines right now. So that 10% case gets really expensive. If I have 10% damage all the time, but for 20 years, they can really add up and do a lot of damage to my blade, where I may end up replacing blades over time. And because the wind turbines are getting so tall, they're actually triggering most of the lightning strikes. And we know from just some early wind turbines offshore in the United States and Block Island and down in Virginia, there's like 7 wind turbines, literally 7 wind turbines offshore in the United States right now, that they're triggering lightning strikes. It's a little bit different. And we don't have all the answers because in the States, one of the issues is this. We're going to put a lot of wind turbines offshore into one of the strongest lightning strike areas that we don't have much data for. We know lightning, if you look on the right, those are lightning strikes that happen on the ocean, on the Atlantic Ocean. There's nothing out there now. It's flat, right? So lightning strikes that occur to flat territory, and they're that strong. What happens when I put a 300-meter wind turbine? Or how about 100 300-meter wind turbines into the middle of that? I think what's going to happen is we're going to have a lot more lightning strikes. And because we're going to have a number of lightning strikes and the frequency of lightning strikes is going to be so high, a 10% damage rate can really add up. And that's where I see the industry right now. And my company and a lot of others like Peter's company too are out there trying to change the dynamic. And the OEMs, you have to give them credit. They're working really, really hard. You may not see it, but they're working really hard to change the dynamic, to make their wind turbines last longer, have better lightning protections, and to save the owners and operators money. And that's a really great step to see. So I've given a little summary just to whet the appetite. But if we have any questions or on wind turbines and lightning protection or where we're going, I'd be glad to hear them.
Yeah, thank you for letting us know about your viewpoint on the topic. Really interesting. As Alan said, if anyone has a question for him, please ask. Now I'll put on my presentation again. No questions? Okay. Is my PowerPoint visible already? Oh.
I see that we have a question from Hans. Are there any stats on how much more or less strikes hit turbines offshore versus onshore?
That's a great question. I think the answer is really still unknown. So I think Europe has a better answer than the United States right now. And in Europe, I know that we're supporting a couple of projects that are offshore projects. Lightning's different in Europe than the United States. What we're worried, and let's speak about India too while we're here. So India seems to be having a lot of lightning damage at the moment, and so does Brazil, right? So these are in Turkey. There's Japan. There's a case study here of lightning strikes. The real question is height. I think that's really the issue. As we have crossed from sort of 2 megawatt machines to 4 or 5 megawatt machines, and now we're talking about 15, 16 megawatt machines, it's only going to induce more lightning strikes. And I talked to a lightning researcher just yesterday that does a lot of studies in the middle of the United States, and I asked him that exact question, like, what's going to happen? And the answer is you're going to have more lightning strikes. You're going to have more lightning strikes to wind turbines. The question is how much and how powerful. And I thought that was a very good answer. We don't know. And this is why Yamatek and Peter here are really important, because we need to be monitoring and measuring those things, because the engineers can't respond until we have data.
Okay, does that answer your question, Hans?
Yes.
Okay.
Okay, thank you, Hans. Great question, and thank you, Alan, for answering the question. Okay, then we will go to the next and final speaker of today's webinar, which is Taruka. Our third speaker is Hans van Beek. He is the CEO and one of the founders of Taruka. Taruka is developing a solution to monitor and predict 365 days per year the structural health and condition of wind turbine blades, enabling optimized predictive maintenance and lifespan planning for these blades. In this way, Taruka is reducing the need for scarce human and capital resources for blade inspection and maintenance, enabling the scaling up of the offshore wind energy capacity. Taruka is currently operating from the high-tech campus in Eindhoven in the Netherlands, and we will now listen to Hans's presentation. So good luck, Hans. If you want to share your screen, if that's possible.
Do you see it like this?
Yes, totally clear.
Good. A little bit daunting to talk about lightning after Peter and Alan, because two experts in this field. We come from a slightly different perspective, and listening to them and seeing, say, how much uncertainty there is, and lightning is a probability, and how complex it is. So we talk about the damage that the electricity from the sky causes to the electricity production from the wind. Oh. Maybe a little bit a different perspective from our side. We are still a startup, only a few years old, are still developing our solution, so can't really sell anything yet. And we take the perspective that we assume that not all lightning strike damage can be averted, even how good the solutions become, especially in the coming years. And we are developing a solution to remotely detect the blade damage caused by, amongst others, lightning strikes. This is a beautiful picture, isn't it, for the wind turbine industry or for the wind energy industry. It's a fast rotating wind turbine, clear skies. Wind turbines have to rotate to print money, or to produce electricity and to print money. So this is a nice picture for the industry when it rotates like this. This is not such a nice picture because the damage to a blade, not sure if this is caused by a lightning strike, but this wind turbine is standing still because of damage to one of its blades. And it's not turning, it's not producing any electricity, it needs to be repaired, and it is missing income for the owner of this wind turbine. So the cost of standing still are huge. Let's say we found a number of around 1,300 megawatts per day when a turbine is standing still. This is slightly higher than the numbers that Peter gave. Maybe I'm negatively influenced by the rising electricity prices at this moment here in the Netherlands. But what it means if you assume this type of cost is that, say, if the new 1 gigawatt wind parks that are planned out there at the North Sea, where they sold the licenses last week or so, at the moment that you have one of those wind turbines, every wind turbine is standing 1 day idle per year while it is windy, what wasn't planned. That's a total of 1.3 million euros. So the cost of standing still are enormous. And according to DNV, lightning damage is the single largest cause of unplanned downtime in wind turbines, and the most common insurance claim filed by wind farm owners. So from that point of view, it seems to happen a lot, even when the statistics, how many happens, I think Alan said 5% of blades get damaged each year because of lightning strikes. That's a lot. Over the 20-year lifespan then of a wind turbine, if you take that as least, 5% every year, that means that for sure every wind turbine gets damaged during the lifetime, or for sure on average. Wind turbines are like lightning magnets. Almost during the whole, research has shown, almost during the whole lifespan of a wind turbine, lightning cracks can be discovered in the wind turbines, in the blades. What is causing it? It's one clue is that lightning didn't hit wind turbines in the research that were standing still. So only the turbines that were turning where the lightning hit. Which is then problematic if you assume that wind turbines have to turn to produce electricity and to generate the money. And this issue of wind energy is becoming, if we look from a Europe point of view, is becoming even a bigger issue. If it is now already an issue. 50% of all electricity in Europe has to come from wind energy in 2050 to achieve the climate goal of 100% CO2-free energy production by then. And offshore, the increase is a 22-fold compared to what it was in 2020. So the increase in overall capacity and especially in offshore are enormous. And then we look offshore, and that was one of the reasons I asked Alan if there were already any numbers about, because we know that for sure the turbines are higher, the blades are longer, there is nothing around there that can pick it up. It's far away from the service points. You have to go there by a boat. There is plenty of salt around the ocean, and one of the research has shown that when salt is attaching itself to the blades, that makes them even more attractive for lightning strikes. So altogether, let's say, with this 22-fold increase offshore, there is an enormous increase in risk and in costs for the impact of lightning strikes on wind turbines. And to manage these risks and these costs, on one hand, we have to protect against the strikes. And on the other hand, we have to detect the strikes. But from our point of view, what we see as well, and that's the other alternative, of the other aspect that we like to bring in here, is that it's in detecting of the damage. Because there is this uncertainty. There is this lightning is a probability, and there is this uncertainty if after a strike, if there is damage, and if it is required to stop the turbine. Because you don't only have the cost of repair, and you have the cost of the inspection, but you also have the cost of stoppage waiting for the inspection or the repair. And I think this is what Alan showed as well. The cost difference between minor and major damage repairs is enormous. There is a factor 60 almost in between. So here they indicate that excluding labor and downtime cost, the material cost could be, for a minor, could be 1,500 euro, and for a big 90,000 euro. And if blades completely have to be replaced, then you are talking about hundreds of thousands of euros. And what has been seen as well is that the cost of untreated damage rises exponentially over time. So at the moment that there is small damage occurred in a blade, and that blade isn't inspected and repaired, and it progresses untreated, then that damage can become later, and this is a probability, of course, as well. There's no certainties there, but could become way much more expensive to repair. So there is an uncertainty here, and therefore, from the point that we see, and to address this uncertainty, it would be really good if there was a way to remotely detect if and when a blade needs inspection and repair, to prioritize the deployment of the highly skilled human resources that need to do that further inspection and repair, to lower the cost of the maintenance and the wind energy, to keep wind energy scalable offshore, and to increase the lifespan of the blades, and to deal with the uncertainty of potential damage after a lightning strike. So, as Taruke, therefore, we imagine a world, and we're working very hard to generate and to create that world, where the blades tell you what their structural health and condition is, and when they need further inspection and maintenance, without requiring wind turbine stoppage, reducing this need for human intervention, enabling optimized electricity production cost and blade lifespan planning. So we are less an expert than what Peter and Alan have presented. We wanted to show that there is, say, another part of, say, the cost of lightning, and that is how do you deal with the damage that is occurring in those blades, and is there a way that you can actually minimize the impact of that damage? It would be even better, of course, if, say, all the damage can be prevented by the solutions out there. Fontys, thank you for the opportunity for us to present here as well, together with the other experts, and I welcome any questions from anyone.
Okay, we have a question from Anastasia. Do you think different companies in the industry should work together more to tackle the issue of lightning strikes?
Question is for me, Anastasia. Yeah, I think it is. I'm not so quickly sure how the cooperation would be, but I think to actually have companies working together and to share research on it and to understand, say, how big the impact is, and especially I think with the move towards moving offshore. This is, I think, as Alan said earlier, let's say when they moved the turbines from California to Texas, that were some unintended consequences of finding the higher wind areas. I think in Europe very much could happen the same. That say there could be unintended consequences of making the wind turbines bigger and bigger, putting them 10 kilometers or 20 kilometers out of the shore, having them there, and then yeah, who knows what happens in 5 to 10 years? Difficult to predict. So I think there is an uncertainty there, and if let's say that is the industry is working together on getting that clear and seeing what the impact could be, that will be useful, I think, for everyone. Also for my electricity cost at the end of the month. I'm not sure if Peter or Alan has another thought on it.
The IEC committee has done a good job of bringing together the different OEMs and technical specialists together to put them at the same table and to discuss some of these issues. And that model that the IEC is using is the same model that's used in many other industries, and it's been very successful. So the FAA uses the same model for airplanes. The Europeans use the same model for airplanes and other industries. That model of bringing the technical experts together, basically locking them into a hotel room or a hotel conference room for a couple of days, has produced results. And so if you look at the IEC standard where it was 10 years ago to where it is today, you see a much better document because those technical experts are in the industry is feeding back that data. And they're making the specifications tighter, better, more reproducible, and we're having better success with it. So it's just going to take, I think it's going to take another revolution sort of change with IEC to get to the next stage, but they're constantly working it. So those things are already happening.
Well, I also would like to give a comment on that. It's my experience that the different manufacturers see lightning protection as a competitive issue. And it's somewhat dangerous to tell the neighbor what they are doing. And there's no doubt there's a requirement to have much more than 5 years of warranty. It has to be extended to, or at least the service warranty to be extended to maybe 20 years. And then it's really a competitive edge if someone is more clever than the neighbor. On top of that, the standards seems to be behind what's really going on. I would love if we could see that the standards were written much faster than they are. But I know there's a lot of stakeholders that would like to have some words in that, and it's really too slow, especially too slow to what we really see out there. One question could be, what is the impact of high charts going through the blades? And it's hard to find the facts for that. The only thing that we can do is that we can measure it now, but it's quite new situation that we are able to measure it. So we need to collect more information. But if we ask as a sensor manufacturer that we should share some measurements in between manufacturers, forget it. That will not happen. So maybe the universities can do something. I don't know. Okay.
Okay. That was a great question. Nice to hear. Yeah, 3 different viewpoints on that one. Let's see if there's another question. Leon, can you?
Yeah, I see that there's a question from Armando, specifically for Alan. The industry is adding more and more carbon to the blade structures, and how can it contribute to damages caused by lightning strikes?
It's a great question because we're living through the addition of carbon to blades. So we add carbon fiber to blades to increase the strength as they get longer. So when you cross the 70 meter-ish, kind of 60, 70 meter threshold, to keep the blade from being so overly massive, what you do is you take out fiberglass, you put in carbon fiber. And carbon fiber is really conductive. There's a sort of a misinterpretation of that carbon is not really attractive to lightning. Lightning is very attracted to carbon fiber. In fact, when we make airplanes out of the same material, those airplanes get struck all the time. It's no different than aluminum. It's the same thing. You're seeing the same kinds of lightning strikes on airplanes and on wind turbines too. The real issue is, how do you incorporate the carbon, this conductive piece, this conductive structural piece that's so critical, into the lightning protection systems? And you've seen two approaches of that so far. You see it integrated as one of the current paths, and you see it not being one of the current paths. Those are different approaches, and they've had different levels of success. The real issue about carbon fiber is, if you do get energy or lightning into carbon fiber and it does get conducted down the structural element, it's going to have to come out. So once it goes in, the lightning has to get out. If it gets out on its own and jumps, like breaks through some of the structure, which is what we're seeing today, the lightning energy jumps out of the carbon, attaches to something else to get to ground. It does really significant structural damage near the hub. And that's where we have seen blades break off, is that we've damaged that integral spar piece, that really critical structural piece, from lightning jumping sort of randomly out of it. And that's where the industry is taking a wide turn. You've seen a lot of that happen over the last 24, 36 months of changes to approach around carbon. I don't think that is solved yet. I think the manufacturers are dealing with it right now and are back in the lightning laboratory doing a lot of tests. And if you watch the research papers being generated, you can see that in Europe, in the US a little bit, very little, and in China. You see a lot of the research happening in China at the moment.
Okay. Great question once again.
We have another question from Austin to everyone. How much more of a challenge is it to detect and or prevent lightning strike damages with onshore versus offshore turbines? Or is the difference more dependent on the height of a turbine?
Yeah, if anyone wants to have a say on this this question.
I can start on that, and maybe Peter can follow me here, Hans can follow me. The difference, I think Peter highlighted this, and Hans will probably chime into the same thing. Speed of the blade has a lot to do with the lightning protection, and I know that seems weird to think about, but there is an impact of the height and the rotation speed, the tip speeds, and the tip speeds have gotten faster and faster and faster as the blades get bigger. You're generating more power. They become much more attractive, and there's a lot of physics behind that, which we don't need to discuss at the moment. But the fact of the matter is, as those tip speeds increase, those tips become more attractive to lightning. And that's going to be a game changer as we go from sort of the 4 or 5 megawatt machines as we move up to the 10s and 12s and 15s. And the types of lightning we're going to see coming from those offshore lightning strikes is going to be slightly different. And Yamatech that measures those will see, or should be seeing, slightly different kinds of lightning strikes happening. More of a wind turbine triggered strike than a naturally occurring a strike.
Okay. Hans or Peter, any comment on this particular question?
Well, it's difficult to have hard facts on this, because sometimes we need to do some guesswork. But I think having our experience in mind, we have some good guesswork. Actually, one of our sensors do measurements on the charts that the blades collect from the sky. And it's quite new. It's a new development here. It's just 2 years old. But the surprising thing is that the blades are pushing around the charts when they move compared to the situation where they stand still. And we have a lot of data showing this movement, how that changes the charts collection. And the surprising thing is that we actually can measure the rain when that drops in. The raindrops themselves have a content of charts. So now we have a new rain detector, but we are not that much clever on that position right now because it's absolutely new. And we hope to be able to establish much more measurements in the near future. The original idea of that sensor was actually to detect if the down conductor was broken. But suddenly we have a new dimension of what we can measure. But it supports the idea that there's a lot of difference between the speed of the blade and the actual charts collection or charts attraction. But there's a long way to go. I would not like to be an expert on this. But we have some interesting measurements for sure.
Okay. Thank you. Hans, any comment on this?
No, I think everything has said. I just see offshore higher wind speeds, larger turbines, longer blades, higher speeds, more lightning strikes.
Okay. Thank you.
We have another question.
Yeah.
We have another question from Hans, specifically for Peter. Can you predictably relate the strength of the current that goes through a turbine to the type and level of damages that it causes?
It's quite difficult to hear you. Can you come closer to the microphone?
Yeah, of course. Yeah. The question is if you can predictably relate the strength of the current that goes through a turbine to the type and level of damages that it causes.
Yes, that's actually the objective for the sensor that we provide, that we measure all the 4 parameters of the strike, meaning that the rise time, the peak level, and the charts. And on top of that, we also have a very advanced calculation of the amount of material that will be melted from the receptors, so that we can tell if you should go and make service or you could stay at home. And that's extremely important for the offshore turbines. If it's just 2 grams of material or if it's half a kilo of material that is melted away. So yes, the answer is yes, we do measure those parameters, like when you go in and make an analysis of your heart, then you make some analysis on that waveform. So yes.
Thank you, Pete. Very interesting.
Thank you for your question and for your answer. I think we have one more question.
Yeah, we have a question from Koen. Does the risk for getting hit and for the amount/cost of damage increase as the wind turbine gets older? The question is for anyone who knows an answer.
I guess I can start off here. The risk as the blade gets older does increase, and there's a couple of reasons for that. The lightning protection system is still there, right? It's the same one that was there when it was produced at the factory. The issue comes about in terms of, like Peter and Hans were talking about, does the down conductor cable inside break, or is there a disconnect, or there's something broken inside? That's a big issue. Other issues is the dielectric strength, the strength of the plastic material, the fiberglass and the epoxy over time as it sees, and what Peter's, I think, finding in measurements is the blades are constantly exposed to lightning or charge almost all the time, particularly in the summer months in the United States. Pretty much every day you're going to be exposed to massive amounts of charge. And that weakens the electric structure of the blade. Now, we think the blade is being this really massively strong thing, and it is still massively strong mechanically, but electrically, not so much. So as the blades age, it adds another problem. And it's sort of the third problem we're seeing, which is industry-wide, is leading edge erosion. Right? So leading edge erosion just degrades and eats away at the blade structure, which makes it much more vulnerable to lightning damage and other repairs that are not finished. So if they have a blade that has been damaged in a minor lightning strike and may have a little bit of a wound in it, the next lightning strike may do a lot more damage. And so as blades get older, I think we need to be paying a little more attention to getting out in there and repairing them sooner, because the blades are just much more vulnerable as they get older.
Yeah, what I was thinking with this question is that, say, it's also the small impacts that are cumulatively over time adding up. So maybe it's everything works perfectly, the turbine gets hit, there is actually no real damage, but there is a little bit, and the next time there is a little bit, and the next time there is a little bit. And if you're going 5 years, 10, 15 years like this, then at a certain moment that little bit could be the last drop in the bucket that is causing the issue. So just my 2 cents.
Okay, great to see your viewpoints on that one as well. I think that's this would conclude the webinar for now. If anyone has any further questions, you can ask them in the chat. If any questions may come up after the webinar, please feel free to email them to lightningstrikeswebinar@gmail.com, and we will make sure to get back to you as soon as possible. I would like to thank Peter, Ellen, and Hans for sharing their views on the subject, of course, and for interacting with each other. I think it was a really nice experience. And of course, everyone who attended the webinar, thanks for your time, and I hope you enjoyed it and learned something as well. And have a nice day. And if you have the time, we have a Google form link in the chat, and you can give your feedback on the webinar. So what went well and what could have gone better, and that would be greatly appreciated. And thanks again for attending, and I wish you all a very nice day.